Hello everyone, I'm Radoslav and today I'm going to be explaining one of the problems from the CodeChef challenge. This time it was like the cook-off and the problem was called hill sequence. It was medium or like hard. It wasn't very hard, but like it requires some combinatorics and dynamic programming and maybe some probability, although it's not necessarily needed to know a lot of probability. Basically just need to know the definition of expectation. And yeah, I guess I'm just gonna start with the problem statement. After that, I'm just gonna go through the solution. And yeah, this video will be definitely shorter than most of the other ones because the problem isn't that hard. All right, so let's go to the problem statement. So the problem is called hill sequence or like hill array, and basically we are given a definition which is hill sequence. And what this definition basically means is that in a way our array looks like a hill if we look at it from both sides. In some sense, if we want to be very formal, we have some position P, which is somewhere in the middle. Maybe it can also be like in one of the corners, but let's say it's somewhere in the middle. And the sequence from the first element to this Pth element is non-decreasing, so it's like kind of increasing, but also you can have equal values. And the sequence starting from this Pth element and going to the end, so like the nth element, it's non-increasing, so it's like kind of decreasing. And yeah, you can look at the arrays. This one, for example, as I said, the P can be also in the beginning, so here P is actually 1, so it's just like simply a non-increasing sequence. So yeah, here you can see that this isn't a hill because it's in some sense it's like two hills. So yeah, we have like this definition of hills, and know that those hills always have length n. N is given to us, it's like fixed in the input. And also we are given m, which will be the sum of elements in our sequence. So in some sense, like we are constrained about the total sum of the elements in our hill sequence. And yeah, basically the problem now is let's consider all hill sequences that have length n and also have sum of elements equal to exactly m. Both of those are given. And we are interested in finding the expected value of a function f applied to this whole array A with some coefficient k, where k is also given. And this function is pretty much, you just sum the kth powers of all elements. It may sound kind of complicated, but the main idea is that you look at all sequences, and for every sequences that are hill sequences, have length n and have sum of the elements m. And after that, for every sequence, you compute the sum of every element to the power of k. And yeah, you, in a way, write down all of those values in a list or something like that, and then you just average them out. And yeah, that's pretty much the problem. And you're interested in finding this value, modulo 10 to the 9 plus 7. And most of the people who are familiar with probability will know that every fraction, in a way, can be the answer in this problem can be represented as a fraction. And you know, like instead of just outputting the fraction, you just have to output like b multiplied by the modular inverse of the numerator. And yeah, that's pretty much the problem. And also you're given, so because sometimes, as you can notice, some of the elements of this sequence can be 0. So like on both ends we can have some zeros. So because like 0 to the power of 0 is generally undefined, in this problem you just consider it being 1. So for simplicity. And yeah, basically that's our problem. And you can kind of care about this mostly because k can also be 0. So yeah, let's look at the constraints, and you can see that n and m are up to like 1,000, and k is relatively small, so it's like around 20. And also you should know that we have quite a lot of tests, so like we have 10 to the 6 tests. And this means that we can't really compute a lot of things for every test, and we need to do some pre-compute. So our solution will pretty much be, we have a pre-compute that saves the answer for every tuple n m k, and then we just, for every test, we just compute the answer, like just print it. So yeah, I mean, the fact that we have a lot of tests should suggest that we need to do some pre-compute. So yeah, I mean, that's pretty much the problem, and let's get straight to the solution. So I'm just going to describe how the steps of the solution would go. First, I'm going to describe how we are going to count the number of solutions, and you're going to notice that counting the number of solutions is like a simpler version of our problem, because when we have, for example, k equal to 1, our sum is always the same. And it's like, I mean, because like we are kind of given this sum. And in a way, counting the number of solutions is equivalent to like, in a way, finding the sum. Although for k equal to 0 and k equal to 1, the answer is always fixed. So you don't necessarily need to count all solutions, but it's a good idea to just start simpler by just considering the number of solutions. And after that, I'm going to just go, basically, we are going to see how to compute the number of valid solutions with like some fixed n and some fixed m. And then I'm just going to explain how to extend this for larger, basically like how to extend it so that we compute the f function with some specific k. And yeah, I mean, we are going to see that one part of, but basically like the solutions will be very similar for 2 and 3, like the second and the third option. But like one of the main problems would be that one of the cases is kind of hard to compute in in the DP for the answer, it will be kind of hard to actually compute one of the cases. And then we are just going to apply the binomial formula in a pretty trivial way. And we are going to see that everything just comes into place. And I'm going to just, yeah, you're going to see. So yeah, let's just start with how to count the number of solutions. So I guess it's quite obvious that we should start with some type of DP, because, I mean, generally you want to count some solutions, and also the constraints just immediately tell you that this is some kind of DP. So let's think about how the hills are actually defined. They're in a way like some mountains, and this could intuitively give you the idea of kind of building the hill from both sides at the same time, because you know that everything, I mean, the left and right elements are basically like the smallest two elements, always. And I mean, everything in between just kind of increases until it reaches the point P. So in some sense, if we have like dp left, right, remaining sum, let this be the number of solutions. And I mean, in some sense, like this will basically just be the number of mountains of this type, which are between positions left and right, and have like remaining sum equal to something. So let's see how to actually compute this thing. And it's not that hard, because we have pretty much 4 cases. The first case is, like, let's consider just the beginning, where left is equal to 0 and right is equal to like n. Actually, left is equal to 1 and right is equal to n. And we have 4 cases, as I said. Probably you have already read them, but like the first case is that we are going to keep the left equal to 0. So this means that this element won't really contribute to the answer or like the counting. So we can just literally move it to the left, but like moving the left border like to the right with +1. So that's like the first case. Then we have the second case where we set only the right bound to 0. So in a way, like we just move the right bound to the left. And then we move like both the left and the right. We say that they're both going to be 0, so we can kind of move them. And the final case is that neither the left nor the right will be 0. And I mean, the first case is a bit more complicated, but like the first 3 cases are pretty much like moving the left or the right with 1. And you can notice that one easy way to calculate this is to just like sum the first and the second case, and then subtract the third case. Because like, let's consider in the first one, we just like fix the left or fix the right, and yeah, we kind of get the answer. But then this means that we are double counting the third case where both of those were like 0. So we can just like sum the first and the second case and then subtract the third case. And this way we are gonna like basically just get the correct DP for the first three cases. And then for the fourth case, it's, as I said, a bit more complicated because we have explicitly decided to have both the left and right greater than 0. So this means that they are at least 1. And this should suggest that, in a way, like, we definitely have everything between left and right being at least 1. Because, as you know, left and right are, in a way, like the smallest elements, and they're like in the corners. So this means that this whole bottom row should always be present. And this is like the main observation. What we can do is that basically we can, in a way, take away everything in between left and right on the bottom layer just now. Because like we know that the sum will definitely decrease by right minus left. So I mean by basically like this bottom layer. And we can just like consider the DP with the same left and right. And we can continue building the DP like that. So in some sense we are going to build the mountain from left to right, from both sides at the same time, I want to say. And the first three cases are easy. And for the fourth case, we can kind of, we know that we want left and right to be greater than 0. So we can just take away now the whole like bottom layer and consider the DP with like without the bottom layer. So like just this top part. And now that here we are gonna still we are gonna keep the left and the right the same, so that I mean, because like we can imagine that here we also had like an element, so we could like again remove one layer, and we just wanted like at every step we just want to remove a single layer. So yeah, I mean that's pretty much like the DP, but like you can notice that right now it's actually cubic because the left, right, and I mean left and right are up to n, and then like the remaining sum is actually up to m. So it's like n squared multiplied by m, and as you remember, the constraints were like n and m were like up to 1,000. So we need to notice the fact that actually we don't really need to keep left and right because we don't really differentiate between them. We just care about the length. So in some sense, like we just care about the difference between right and left. Why? Because like in the first three cases, we never actually, I mean, we are always interested in the length because like we just keep zeros. So, I mean, we don't really necessarily need to know whether we remove the left or we set the left to 0 or the right to 0 because like the both cases are pretty much the same. While here in the other transition, you can notice that the difference always depends just on the length. So this means that we can just have like dp length and remaining sum, which now is quadratic, like the state is quadratic. And you can pretty much see that the transitions are again quite simple. I mean, obviously for the fourth, like the last transition, which I mentioned with taking out the last layer, the bottommost layer, obviously this transition is the same. I mean, we have no change in it compared to like previously. We basically just have length here instead of left right, and length here instead right minus left plus 1. So yeah, the last transition is very easy. And for the first three transitions with like moving left and right, I already like kind of explained the intuition why it doesn't matter, but like formally we can just have like 2 multiplied by the dp of the length minus 1. This means that we are just moving one of the dp's. This means that we are just moving one of the borders, either the left one or the right one. So this means like we just set left or right to 0 and decrease the length. Because they're 0, the sum remains the same. And yeah, we have multiplied by 2 because we can either remove the left bound or the right bound. And again, because of this double counting of setting both the left and the right to 0, we need to subtract the answer when we have decreased the length by 2. And yeah, this is pretty much when we set the left and the right both to 0. So yeah, this is pretty much the transition for the first three cases. It now becomes just a single thing. So yeah, I mean, to recap, right now we are gonna have like a dp for the number of valid solutions with some fixed n and some fixed m, and we are gonna compute it in O(n)m time. And I mean, if we just compute it for the first 1,000 n's and the first 1,000 m's, like this again would be in O of around 1,000,000, then we are gonna have like this pre-compute. So yeah, I mean, pretty much the main idea for like the whole solution is that we are again gonna build up our solution by layers, and I mean from both sides, although we are gonna just keep the length. And there will be like two cases. The first one is pretty much you set the elements to 0, like the corners, and the second one is pretty much like just taking out the bottom row. But here the main trouble comes from the fact that actually when we remove the bottom row, it's hard to keep track of how, I mean, here we have like the sum of the elements to the power of k, and this is actually kind of hard because in a way this means that I mean the power k kind of depends on the elements by themselves, so it's kind of hard to figure out how exactly we're going to do this. And basically it turns out that we can use the binomial theorem or like binomial formula, there are different names, and yeah, I mean that's pretty much how we are gonna compute this sum of answers in an easy way. So yeah, as I said, this DP will be quite similar. It will pretty much be like answer, which will be the sum of the f's over all possible hills which satisfy the constraints, like the length is fixed and the remaining sum is like basically the current sum. And also we have this additional parameter k, which represents the power basically. And I mean, k is like less than or equal than 20. And clearly like the complexity will be nmk if we do like the transitions in a fast way. I mean, yeah. So the actual complexity will actually be k squared because, yeah, you're going to see in a bit. So we have basically, again, two cases. As I said, we are going to keep the structure of the DP. The first case is like we either move the left or the right. And the second case is like when both the left and the right are non-zero. So in a way, like we need to take away the bottom, yeah, like basically the bottom row of the hill, and we kind of take away it and consider the top DP. But it's hard to like do this when we actually have powers of k, because the powers depend on the relative sizes of the elements, and it's kind of hard. But yeah, I mean, for the first case, I guess you could kind of figure it out, but it's pretty much the same as the case for counting, because when you consider something as 0, 0 to the power of k for like k greater than 0 is trivial to compute, because it's always, I mean, it's always 0, because like 0 to the power 0 cubed, 0 square, everything's like 0. So I mean, when you move the things, it's pretty much like the same transitions as in the first case, but like you also have like this argument k, so you just keep this argument k the same while computing it. And yeah, I mean, the first case is just trivial. Now the second case is like the interesting bit, and it's basically about like how are we actually gonna do the movements in some sense, like movements upwards when you consider like the layers with everything fixed. So this is in a way like the trickier part of the solution, and what we need to do is like we kind of know that everything from left to right is I mean, okay, so we want everything from left to right to be non-zero right now, because like we don't really have left right, we have like just the length, but in a way we just have everything between left and right non-zero. And this means that they're at least one, so we can again take away like the bottom layer, and let's express every position ai to the power of k. But like obviously let's just get every ai and express it as 1 plus ai minus 1 to the power of k. This is like a very like obvious transformation. It's, yeah, you basically just add 1 and just subtract 1. It's obviously the same. it may sound kind of, it may look kind of weird, but the main reason we are doing this is because like this +1 in the beginning is because we take away this bottom layer. And you can notice that this AI -1 is going to be the height of basically like every position in the hill after like we remove the bottom layer. So in a way, like it will just be the height of this top thing from above. So in a way, this means that if we actually open up the brackets, this suggests that we are just going to have like an expression which depends on this top part. And that's pretty much what happens. And what we need to apply in the end is basically just the binomial formula, which probably you're familiar with. When you have like x plus y to some power, it's just like a sum of basically like the binomial coefficients. It's a very famous formula. And yeah, what we notice here is that we can basically just open up the brackets from here. And what we are going to get is that we are going to have like this transition. So here it should like plus equal, because I mean, this is just the other case, like the second case. And what we are going to do is basically we just need to fix every I which is less than k. And we are going to get like our answer as an expression of answers with smaller k's. And yeah, I mean, we need to multiply the answer. If you like go through like details on paper, it's pretty easy to get it. The main idea is that you apply this transformation, you open up the brackets. I mean, you're going to have a sum because here we have a sum of every I between left and right. But overall, if you just apply it, you're going to get that the answer kind of depends just as the sum of the binomial coefficient multiplied with the transition, but with some smaller I. So yeah, I mean, this way we reduce our answer from some k to a smaller k. And I mean, here we have some dimensions. And note that this loop is actually in OK time, because we kind of need to go through all i's less than k. So the total complexity right now is we have n times m times k states. So that's like nmk multiplied by k, because we have k transitions for every I. But that's again fine, because I mean, this is like actually k over 2 on average, because we always just consider the i's which are smaller than k. So overall, this is like a million from n multiplied by m multiplied by 20 multiplied by 20 for this inner loop over 2. So it's like 200 million, which is supposed to pass. And it's like, depending on your implementation, it's definitely going to pass. Like if you implement it well. And that's like the intended solution. So yeah, I mean, maybe you have already figured, but there is one corner case, because we can apply this thing only if we actually have smaller k's. I mean, if k was, for example, 0, how could we actually do this transition? Because then we wouldn't have had like any possible case. So any possible i's, because I mean, there are no integers less than, yeah, I mean, there are no integers less than, no positive integers less than 0. So yeah, I mean, there's like this corner case, which is k equals 0, but you can notice that the answer is always equal to the length. So like our answer is, because like, I mean, it's mentioned that 0 to the power of 0 is defined as 1. And yeah, our answer will always be n, so, or the length. So in some sense, like dp, the answer when k is equal to 0 is just like the number of possible solutions multiplied by the length. And yeah, that's pretty much it. We consider this case separately, and then we build up the other case starting from like 1 using the binomial formula. And yeah, I mean, this means that the full solution is pretty much, we pre-compute the dp table and the answer table, where answer as, again, like the dp is the number of solutions, the answer is the sum of f's overall solutions. It's not really the expected number. So finally, for every test, we kind of need to output like the sum of overall valid hills and multiply by, actually, in a way, divided by the total number of solutions, which is just equivalent to multiplying by the modular inverse. And yeah, that's pretty much the solution. The complexity, okay, here I actually have a typo. It should be k squared, because this is just the number of tests, and t log is just like, I mean, this is the first part is basically like the number of states, and we have like k transitions for each of them, so we have k squared here. And we also need to solve every test. And I have just written log because I assume that we are computing modular inverse in logarithmic time. There are like faster ways to do it, but I mean the most trivial way is just powering to the power of the modular minus 2. So yeah, I'm just assuming that we are using fast power to compute the modular inverse, and this way it's, yeah, we have like this complexity, but with like k squared. And that's pretty much the whole solution. I hope you enjoyed, and yeah, I mean, as a final comment, I guess there are some DPs which are done in this way where you kind of, I mean, in a way, like the tricky part of this problem was to fix the last transition, which was like both the left and the right are non-negative and non-zero. So this means that we can kind of take away the whole layer between left and right at this current moment instead of like doing it later on. And I mean, this basically solves your problem, like the whole problem, because after that it's pretty much details. The more experienced participants will probably like know that trick with like reducing a solution for some k to like smaller k's. So yeah, I mean, the binomial formula trick is quite popular. So I mean, the interesting part of the solution is actually building the initial DP and how you're gonna actually take away like the bottom layer, which is also like not that hard. So yeah, I hope you enjoyed.